Good. So a great pleasure to welcome our emeritus colleague, Simon Saunders, to speak to us this afternoon. Simon, of course, studied physics and philosophy as an undergraduate, then went to Chelsea College in London to study for his PhD in philosophy of physics. Chelsea College, of course, being such an important element in the development of philosophy of physics in the UK and internationally, quite possibly. Before returning to Oxford as a JRF at Wolfson, spent a good number of years at Harvard, and then again returned to Oxford in the mid-90s to be reader in philosophy of science and latterly professor of philosophy of physics and tutorial fellow at Merton College. Simon's work is, I expect, well known to everybody here, but it covers all the major interesting things that there are in philosophy of physics, I should say. But Simon's perhaps best known for his work on the Everett interpretation, where he's played arguably the central role in moving the Everett interpretation into a defensible and possibly even believable position. So, a non-trivial achievement. So we're going to hear the latest, though. I mean, a lot of Simon's work on probability and the Everett interpretation has been hugely important. But here's the latest round. So over to you, Simon.
Well, Chris, thank you. That's a very kind introduction, and thank you all for coming. Much appreciated, especially for me to talk on this topic, which is dear to my heart. So it's a bit of a jigsaw puzzle, indeed, as my image shows, and some of the pieces only really came clear to me. And of course, I could be deceived. It became clear to me in the last few months, and that's really what I want to spend time on. But I'll go through individual pieces. And one of the latecomers, actually, to the jigsaw puzzle is next slide. Yes, is Gibbs, who I had never thought, a colossal figure, of course, but I hadn't thought engaged in any immediate way with Everett. Now changed. Okay, so why probability at all? You might have thought that these questions have been decisively dealt with and concluded, especially by David Wallace in his remarkable book, The Emergent Multiverse. But for debates about probability solution, advocated by David, and also by David Deutsch, though in a rather different way, the book Many Worlds is a great collection for argument. I'm particularly proud of the transcripts of debates, and I do think they're fun. Say things that reveal their inner selves in ways that they don't when they write things down. So, and just my take on the decision theoretic route to probability in the Everett interpretation, I think it's an extraordinary achievement, a historic first, but I don't think it solves the puzzle of probability. What it does solve is the puzzle of why on earth credence should connect with something objective in the world in the way that it does. But it doesn't, what it fails to do, it seems to me, and this is partly through meeting so many people who love it, that it doesn't explain probability or phenomena, rather. It doesn't explain statistical phenomena. It explains maybe why agents expect to see such phenomena. It's the content of David Deutsch's arguments in favour of it. But it doesn't explain the phenomena themselves. And this is very much the content of David Albert's brilliant critique of the decision theoretic route, which is in the Many Worlds book. Okay, so that's why it seems to me something more is needed. My own work in the Many Worlds book rather looked at several criteria pointing to squared amplitudes of branches as being objective probabilities, the decision theory argument being one of several. But that didn't seem to persuade many people. So there we are. Okay, so new ideas. So first piece of the jigsaw puzzle is frequentism, especially finite frequentism, that most people think is a dead duck. So it's a little bit surprising to think that, oh gosh, one can actually do something with this. The doctrine, I hope, is familiar to you all, that the probability of an event is the relative frequency with which that event occurs in an ensemble. I think one of the great virtues of the approach is that it automatically satisfies Kolmogorof's axioms. Now, I say that with some hesitation about countable additivity. But I'm not using infinite ensembles, so I'm only looking at the finite tree axioms, and it certainly explains finite additivity. And it's got to be the quickest ever explanation of why probabilities are between 0 and 1. Right? The frequency in ensemble, it's the number. Oh, anyway. Okay, good. So, and I've got a picture there, Richard von Mies, who's probably the most well-known proponent of the approach in the 20th century, although it goes right to the early 19th, I think. So perhaps could be. There's various other people. Venn wrote a fairly comprehensive analysis of what it was really saying and what it was claiming and so forth. Now, another piece of the puzzle, Boltzmann's microstate counting rule. So this was introduced by Boltzmann in the 1870s, I think 1879. The 2 or 3 papers you wrote about then that all had it. And the 79 paper in particular, I think, is often thought, I think Dargol even says this, as probably his most influential single paper. And it's all about this frequentism. So it's rather surprising to me that recently a very eminent philosopher of physics with whom I have enormous respect, who knows a great deal about this history, who recently wrote a book on philosophy of probability with a chapter on frequentism that did not mention Boltzmann. So I think this is rather striking, and I'm slightly puzzled about it. And I think perhaps it's that it's just really seen as either trivial or wrong by contemporary philosophers of probabilities. So what is it? Well, you divide phase space into cells of equal volume, Liouville measure, and the microstates are those cells accessible to the gas, and we imagine that a gas represented by a point that is wandering around in phase space. So microstates are those equivolume cells accessible to the gas, so that gives you some integer n less than z. Z is just the number you get carving up the phase space. And there I've just stated again finite frequentism as Boltzmann. It's not word for word Boltzmann, but it's what he was claiming. Okay, so some formula there that you may know and love, combinatorics formula that come out of this. And I think it's probably a lack of interest in the combinatorics that is responsible for lack of interest in a way in Boltzmann's frequentism, because you see what Boltzmann did is take the infinite limit as the size of the cells goes to 0, and the number of microstates then goes to infinity, indeed uncountable infinity. And I think the conventional reading today is that, well, if you're going to do that, you might as well just use the volume measure and be done with it. Something like that. But it's worth saying that these formulas, especially this one, this was of crucial importance to the discovery of quantum mechanics. I'm sure it was irrelevant to Einstein's initial, although this was very important to Einstein's initial 1905 paper on the photon. This was irrelevant to what Einstein did in 1905. But it became fairly central to what he did later, including his papers on the Bose-Einstein statistics. And of course, it was central to Planck in 1900. So it was very important to the discovery of quantum mechanics. And I think that ought to give us pause, that a technique that was so important as this maybe should have some respect accorded it. Einstein certainly accorded it respect. I think it was a piece of a jigsaw puzzle for him. That's why I've left the piece up there. I do that. I won't read out what he says, but he's saying the idea appears to me to be of outstanding importance. And here, this is in 1949. Considerable time to reflect.
So before we go on, I'm confused. So in finite frequentism, we normally have an actual ensemble, and you look at the actual frequency in the actual ensemble. Here, are you doing hypothetical because not all the microstates, only one microstate is instantiated?
Absolutely. And another reason why as a philosophy of probability, it's not looked on with great interest, because look, it's hypothetical frequentism, even if finite. And what's the point of these imaginary things? So yes, absolutely. I think it's worth understanding why something that, well, claiming it's important, why has it been ignored? Why has it been uninteresting? I think that probably is one of the key reasons that it's always seen as a version of hypothetical frequentism. Okay, so here's another very important piece in the jigsaw puzzle. a decoherent history space replaces phase space. And by this I really mean the decoherent history space as in Gelman and Hartle's work. Here's Jim Hartle and Murray Gelman. Jim Hartle, dear friend, only now recently departed, but I never met Murray. He was supposed to be very hostile to philosophers. So. Anyway, so what is it? So those that you don't know, I'll just do it in angle bracket church notation. M is a parameter space, the analog of phase space. So it's always the spectra of some commuting set of self-joint operators. Lambda is an additive dimensional, usually dimensional measure on M. H is the Hamiltonian, psi is the total state. So those are the basic ingredients. And for those who don't know anything about decoherence theory, I suggest you just don't bother to try to learn anything now, and I won't say anything, other than that in a context-dependent way, we have something like phase space in quantum mechanics. And the basis of that space may be different depending on the kind of decoherence that's going on. But when you're getting up to Avogadro numbers of molecules, and they're all fairly heavy molecules and so forth at ordinary temperatures, it's always the same decoherent history space. It always consists in heavy degrees of freedom, well localized in position and momentum space. So when you get up to macroscopic, all of these molecules really are moving around just as we always thought they were, with definite geometries interacting with one another, with reasonably definite positions, and so on and so forth. Of course, as soon as you go off to individual atoms, and as soon as you get to light atoms, then everything, and if you go, the temperature goes too low. But in the ordinary world and so forth, you can just think, in a way, you may as well think that the coherent history space is just very like phase space.
Simon, could you just, I might not be the only one, what do you mean when you say some value of commuting self-adjoint operators?
Spectra, oh, I'm sorry, this is a bit of a misprint. In terms of the spectra or the values of commuting self-adjoint operators. Amazing how one misses misprints even though we're looking at something 20 times. Okay, so, and I'm just reminding you all of how it goes, how you go from cells in, well, now decoherent history states, the manifold M, to states, and how it relates to six-threaded operations, intersections, and unions. So for any cell alpha, the associated state is just a cell and usual relationship, disjunctions, and contractions, sections. Okay. Let's see, I think I ought to add that I am using the simplest sort of decoherent history space, which does use projection valued measures. Now, there are other kinds of decoherent history spaces which uses positive operator valued measures, and that's an area very much worth working on, I think. Certainly it's up there in my priorities as to what. Okay, so here's another piece of the jigsaw coming up. Really, I'm sure others have had the idea before, so I don't think I'm the first, but I haven't been able to find anybody else saying it. So reflecting on what Boltzmann did, this business of volumes, why not do something a little different? Divide them so they have the same Hilbert space norm or the same amplitude. Looking at the Hilbert space norm as something like Liouville measure. That's the key idea. In retrospect, I think it was a very bad idea to compare the Hilbert space norm to Liouville measure, because I think they're actually very different functions, and they will in the rest of this talk. But the point of this equi-amplitude representation, I would ask you just to meditate upon these equations for 30 seconds or something. Convince yourselves that you understand them and correct. Okay, so it's saying that for a set of states phi running from 1 to n, if k of them are eigenstates of a projection onto delta with eigenvalue 1, and if the remainder eigenvalue 0, then the expectation value of the projection operator is just the ratio of the number of eigenvalue 1 to the total number.
The phi's are orthogonal. Right? Or the different phi's are orthogonal.
Yeah, they're all orthogonal, sorry. Always dealing with, all of these cells are disjoint from one another. All associated states are always orthogonal. And exactly orthogonal too, not an approximate orthogonality as you have with quantum histories. All right, so I hope you've persuaded yourselves that this is correct, and because it underlies absolutely everything that follows, although I don't need to do any calculations with it. Right, so here was my attempt to put these pieces of jigsaws together as of 3 or 4 years ago, and cognizant of the fact that we're only going to get rational numbers out in this way. How do we get to continuous Born rule quantities? Well, you've got to take some sort of infinite limit. And here's an infinite limit. You consider a chance event that happens right now, say. Now consider all of the histories of the universe that contain my snapping of the fingers, this particular time, this date, month, place. All of the histories, asymptotic time limit, contain this event. So count those. You can count all of the histories, including those that don't contain my snapping of the fingers, this time in this place. So there you get an infinite number of histories, and ratios will then give you a continuum limit. So that was the idea, and the pieces of the jigsaw puzzle, as you see, don't quite fit together properly. Something not quite right, and I sort of knew it at the time, especially if any of you bothered reading. There's a bit at the end where I go over the history and the discovery of the Planck distribution, where you're really looking at the finite dimensional subspace of Hilbert space, or actually it's the summarized Hilbert space because you're looking at bosons. And I said something there that was just flat out false. Terribly embarrassing. But anyway, and I only realized it was false later, of course, but I was uncomfortable with it even then.
Sorry,
Okay.
so you're assuming that all these cells, if they're orthogonal at one time, they're going to be orthogonal for all time in this last analogy that you made?
In the quantum histories thing,
Yeah.
well, the quantum, you're, at each time you're doing a different breaking down into cells. You can, but I want to avoid the histories stuff. What everything that follows is going to be purely synchronic, happens at an instant in time, and you can think of it as an instant following a measurement. Okay, anyway, so cross out this, I got the wrong thing. So go back and think again, just what did Boltzmann do? But now pose the question, and this is really the missing piece of the jigsaw, what if you try to do something similar using Gibbs? And as briefly explained, so Gibbs talked about infinite ensembles, counterably infinite ensembles of gases, endowed with a certain non-negative real function. That's how they come. And then that non-negative real function, he called it density in phase. So that he used to define numbers of elements in the ensemble in a given region. Here it is. D is the density in phase. So consider the numbers. Integral of D over some cell will give you the number of gases in the infinite ensemble. Yeah, that's what. So now he's breaking. What we want to do something similar to Gibbs is break it down into so that these are all equal. Choose the alpha 1, alpha 2, and so forth, so that they are all equal. I'm sorry, that should be in there. And then you will have microstates similar to Boltzmann's finite number, which would be equiprobable by Gibbs lights. And then you can do finite frequentism with those. And everything is exactly the same, really, as with Boltzmann. But you'll notice this bit is missing. There's no need, and this relates to very fundamental structural differences between Gibbs and Boltzmann. But let me not try to encapsulate what those differences are, but just note it. Okay, So now, obviously you can ask, well then what would quantum ensembles following Gibbs be? But I've already got the answer, the equiamplitude thing, so this is not new. I'm just writing it out again. But the point of this, also it goes on to give the same finite frequentism, the point is to better have a comparison of this to this, understand really what is being claimed, and in particular whether there's question begging, and I'm assuming what is to be. So that's my main worry with all of this. One of my most embarrassing experiences I've ever had giving a talk took place a year or two back, where I gave the talk. I was very happy with my talk. Somebody came up afterwards. He was a very bright guy, and he said, so this is a bit of a joke, right? I was so shocked. And I thought about it, and I thought, oh my God, so it is my worry. We'll look at it at the end and see whether you tell me that it's... Right, so having done that with Gibbs, we've got... we had many hours of debate about it afterwards. Anyway, so now, of course, having done that with Gibbs, we can say, well, what is the Boltzmann equivalent? Here it is, the classical stuff again, and there's the quantum equivalent. So this, assuming it hasn't appeared before, it wasn't in my previous paper, I don't know. Very straightforward. And it bears some relationship to what is called the branch counting rule. It was written down in 1973 by Graham in the DeWitt and Graham edited volume on the linear theory. It was supposed to be not a decisive objection against Everett, but a reason to do better than Everett had done, which Graham then proceeded to try to do but failed. So the result was that, my gosh, then this became an absolutely pulverizing argument against Everett. Pretty straightforward branch counting. I mean, even someone like Tim Maudlin will agree that this defines a notion of probability, but it doesn't agree with the Born rule, so you've had it. So what that Graham rule consisted in was similar, except you're not talking about equivolume macrostates. You're talking about macrostates corresponding to experimental outcomes. It was just on the one. It's the point about the amplitude being non-zero. Okay, so that would be the Boltzmann rule. So as a result, we've just got two different quantum rules, two different kinds of quantum ensembles and so forth. So call ensembles defined by either of them admissible. I don't mean by that I'm either talking about the Boltzmann one, admissible. I'm talking all about this about the Boltzmann one, or I'm talking about the Gibbs one. Okay, so I could have Boltzmann admissible or Gibbs admissible, but just to keep it short, I just say admissible. All right. And go back to what was driving the thing along. And notice I've got a huge problem because I don't have the asymptotic infinite time limit. What on earth am I going to do with only finite numbers and only with rational numbers and so on and so forth? So this situation is not normal. You've got ones that, microstates that don't satisfy conditions here. Microstates that are not eigenvalues of the projection onto delta. Eigenstates, of projections onto delta. So call them indefinite on delta, just a bit of terminology. And of course, they're all over the place. I mean, I've just given an illustration here. If you were partitioning up the manifold M by just take the equi-area cells, just do it all in 2 dimensions. And here's my macrostate delta. Well, if I've managed to exactly partition M, the only way I could also exactly partition delta is if the area of delta divided by the area of M is rational. Won't be. So just to illustrate, this is absolutely endemic to the approach. You are not going to get away from these Schrödinger cat states, is one way to put them, vis-a-vis delta. All right, but the point now is that from an Everettian point of view, there's absolutely nothing wrong with such microstates. I mean, it's fine. It's superpositions, macroscopic superpositions, meaning superpositions of microstates that differ macroscopically. I mean, that's bread and butter to everyone. So it's fine that they're there in the ensemble, along with microstates that do, which macroscopic properties are value definite. It's fine that among them are these Schrödinger cat type states. And there's nothing wrong with the probabilities they define. This was the key thought. Even the Schrödinger cat state itself has a probability if it occurs in an ensemble, and other states in the ensemble, admissible ensemble, probability is 1/n. So what is the problem with them? It's this, that if they're indefinite on delta, then they contribute neither positively nor negatively to its probability. 3 out of 10 clearly in delta, 4 out of 10 clearly not in delta, but then there's 3 left Schrödinger cat states for delta. What do we do about that? So here's the idea, and again, I think it's fairly trivial, and I'm sure it already exists in the literature. It may even have a name, and somebody can help me tell me what it is. Might it be called a quasi-probability? Anyway, I'm not sure. But the idea is to define interval probabilities. Probabilities as intervals. So if m out of n microstates in an admissible ensemble are in delta and r are indefinite, some are such that m plus r is less than n, obviously, then the probability of delta is this. And that includes exact probabilities as a special case when r equals 0. And it's easy enough to add and multiply interval probabilities in all probabilities in this implementation. And then the crucial idea is to just require that every interval probabilities fix at delta, any delta. All the interval probabilities defined by any admissible ensemble are consistent. So this is the huge step that's missing in any version of finite frequentism in the traditional sense, something like von Mies. Because with von Mies, you've got the probability is always relative to an ensemble, and you get zillions of different probabilities, but there's just never a question that they're all consistent with one another. Or it would be lovely if they were, but no one's ever dreamed that such a condition could be made or could work out. Okay, so let me now just list the definitions and give some stabs at meaning that I hope you'll agree with, but being philosophers probably endless discussions about the wording, and that goes on in my mind too. Anyway, so the 3 definitions then, the one I've just given, what is an interval probability? Now a definition of what it is for a set of interval probabilities to be consistent, answer if their intersection is non-zero. If all of the interval probabilities were exact, that would just say that all of the probabilities are the same. If they're interval probabilities, that the intersection must be non-zero. And then a counting rule is consistent if and only if for any delta macrostate, the set of interval probabilities that's defined as consistent. This is a huge set. I mean, they may be finite, these ensembles, but continue infinitely a number of different ways of picking them out. Anyway, so here's my meanings. So if I tell you that I've got an interval probability for delta, I'll take that to mean, then you tell me what these bounds are. I'll take that to mean the probability of delta is at least n of 1n, no greater. And then I'll get an uncountable infinity of people who will tell me different facts about the probability for delta, and they'll all be consistent with one. Every single one. Right, and a way of cashing out what consistency means is that one of these may be true. You can see that there's questions about that. Run with this for the moment, right? And ditto that. Right. So
there's a comment from Jacob Baranda saying that probability intervals are called imprecise probabilities.
Really? They're well known, of course they are. I used the very terminology myself in an early version of the paper. Thank you, Jake. That's a super quick correction, my word. It's bad enough having Google, but we've got online experts too. Anyway, so an immediate result of this sort of stuff is theorem. that every admissible ensemble consists of microstates that are superpositions of members of some fixed set of orthogonal microstates. So microstates, you've got elements there. Then the associated counting rule is consistent. It follows straightforwardly from additivity at that level of the elements, because every ensemble is going to be constructed out of those elements, and additivity at the element level will force consistency right through. So this immediately shows something really rather important about this whole approach, that if you're just looking at a finite dimensional Hilbert space, finite operators with discrete spectra only, then you will have elements, right? And the Boltzmann rule, for example, would apply. And would be just fine and would deliver results different from the Born rule. So there's really a constraint here, but there is a way of solving this, getting around this constraint. There's a way of getting around it, which I'll come on to right at the end. Okay, now, of course, the reason this isn't damaging to what I'm saying is because if you do have a self-adjoint operators with continuous spectra, position, momentum, and so forth, then it's absolutely obvious that there can't be any such elements. Because you really are just dealing with the plane and the plane. Connected regions of the plane. The point of a plane will not be the state. It's a delta function. Delta function isn't square integral. Not. So you've got to have non-zero regions of non-zero, whatever the measure is on manifold M with the decoherent history space. David is saying the same thing. Repetitive enough. So we've got this business, but it doesn't really apply unless we want to deal with discrete operators in finite dimensional Hilbert space. So observe this, that the consistency condition implies, when delta is exactly partitioned, that every ensemble in which it is exactly partitioned had better deliver exactly the same relative frequency, exactly the same probability. Okay, but then it's easy to see that won't be so. The Boltzmannian rule. So just take the simplest case of M. You partition it into three macrostates, all with the same volume. This is the Boltzmann. And you suppose the corresponding branches, I meant macrostates, sorry, this is cut and pasted from somewhere, all have non-zero amplitude. So they all count. Well, then from the Boltzmannian rule, the probability of all three of them, the probability of each is 1/3. Right? Frequentism. Now keep beta 1 fixed, vary the shapes of the other two to obtain a new partitioning, again with equivolume macrostates. And it must then be the case that this equality follows. And evidently, at least one of them must be non-zero, the microstates. Is this true? Okay. So some of these two things must be non-zeros. So one of them must be non-zero. But there's no reason at all why they both have. If only I had a whiteboard, I would draw on it here. Well, I did. It would be out of range of people watching, so it'll be annoying. But look, it's very, I think you can visualize it, can't you? Well, here, imagine a circle and 1, 2, 3. So it's just like spokes of a wheel, 1, 2, 3. And suppose the support of the wave function it covers one of the three quadrants, one of the three cake slices, and suppose there's a volume equal to that, which is well, if it's all of it. Let me see, getting this wrong. I really need to draw it. What it's got to do is it's got to overlap one of the spokes. That the support of the wave function, if it overlaps one of the spokes of the three spokes, in that case, then only two of the regions, equivolume regions, will have non-zero amplitude. So the probability now of beta 1 will be 1/2, whereas before it was 1/3. Contradiction. Okay. And theorem, the Gibbs counting rule is consistent. And it's sort of interesting to look at where this goes wrong with the Gibbs rule. I mean, do the same, excepting, of course, they're all going to have equiamplitude. So we vary the shapes of the other two in a new partitioning, but it's got to be equiamplitude. And because beta 1 is one of them, its amplitude must be the same as before. Therefore, by the equiamplitude rule, the other two must have the same amplitude as before. So there'll be three microstates, admissible ensemble, and the probability would be exactly the same as 1/3, 1/3, 1/3. So this kind of example simply won't work. But there's a quicker way to see why. Of course, it must be consistent with it must be consistent because the Born rule, whatever the Born rule quantity is, it's always contained within any interval probability using the Gibbs ensemble. And therefore, the intersection of all the interval probabilities must be non-zero. It must contain the Born rule quantity. So you know it's consistent. Okay. So that's my jigsaw. And it's incomplete because there's lots of unanswered questions, but I think it does capture the importance of looking at it in the Gibbs way. So it's that when you finitize Gibbs in the way finitizing is that a verb? I don't know. Anyway, the Gibbs ensemble is the quantum wave function written as a superposition in the decoherence basis, meaning the manifold M. Decoherence basis, whenever you've got continuous degrees of freedom, it's never a basis. The position basis is not a basis. So that is the ensemble itself, and the density in phase is just that. And then so the entire Gibbs analysis goes through, as far as I can see, unchanged and delivers probabilities. Okay, but here are the questions that are unanswered. I'd like to know how much time I've got.
Oh, ages, about 23 minutes.
Amazing. I haven't given the talk before, so I didn't know how much time it would take. Taken much less. That's great. I can spend more time on giving provisional answers to these questions, but I don't have final answers to any of them. And I think they're all interesting and open-ended questions, which is rather nice. You know, sometimes I hear the sort of talk where you've got to close down the questions because otherwise you're in trouble. I may be in trouble. I think these ones are really open-ended questions, and I would welcome. The first two would close down the talk. The first two do, so I better worry about those two. So, are there variants of the Boltzmann rule that may yet be consistent? Of course, that would floor me. That would render my whole useless. The whole thing would be useless. And this is open-ended in that it's just an ongoing challenge, really. Come up with it. And of course, there may be variants neither Boltzmann nor Gibbs, something else entirely, you know, which is equally compelling. Of course. Let's see. And if they exist, then again, and they deliver something contrary to the Born rule, then that also would spell the end of my any interest in my talk. But let's just look at this variance of the Boltzmann rule. And here's one. Okay, so how about you modify the rule so it applies only to the region on M on which psi, as a wave function, so this is an M-valued square integral function, I'm looking actually at the square amplitude, is non-vanishing. So you take the support of the wave function on M, take the support of it, and you do everything that I was saying before, but just working with that support. That support replaces, as it were, M. That's the sort of idea. But the trouble is, it's a very interesting question, is what is the status of states that, so here's the green is the support of the wave function. What is the status of, here's a cell which overlaps on the green. So if you project out from the state, you'll have something. It won't be, it's a state, it's a microstate. It's being excluded from the ensemble, And it's a microstate, so you might know, what is it? Previously, we had states which were indefinite with respect to properties, Schrödinger cat states with respect to properties. But a state now which is indefinite in this new sense would be something like indefinite as to existence, the superposition of existing and not existing. And this is an interesting metaphysical idea, and I've never come across it before. I mean, it's not, you could think of it as a superposition of existing and being blown to smithereens or something. That's a way of not existing. But no, the blown to smithereens are still smithereens. Okay. So the interesting thing is now a superposition of existing and absolute nothingness at all. So I don't really know what metaphysical sense, if any, can be made out of that. It could be fun. But ask now the further question though, well, all right, you've got some metaphysical sense of that, you've got some story. How are you going to use it as in terms of microstate counting? Okay, and here's the thing. Now, in this case, for this macrostate delta, there's only, I'm excluding all of the ones that are not fully contained within the support. So my ensemble consists of just one member. So the probability of delta is 1. Now, I'm just taking a finer partitioning now, exactly halving it without the alpha primes. And now this cell has picked up, is now included in the support of the wave. And now I've got 2 cells here, also within delta. Now what's the probability of delta? Well, the ensemble now consists of 3 elements, and delta is 2, so 2/3. So I've gone from probability 1 to probability 2/3, inconsistent. So this doesn't work. So you might think, well, I mean, here's another thing you might try to do. What about you just take a wave function? You add to whatever wave function you've got another function, could be analytic function or something that's non-vanishing everywhere except at measure 0. Make its amplitude absolutely infinitesimal, superpose it with the original state. So you can do all of ordinary quantum mechanics with the new state and you'll never detect the difference. What is happening with the Boltzmannian rule, of course, is that, well, you might think you've solved these problems. You have solved these problems. But you've done so because now you've got an analysis of probability that has nothing whatsoever to do with the state. There's nothing to do with the state. You're just messing around with Liouville measure, or rather the measure on manifold M of the decoherent history space. So I think you're just turning your back on what is the project. Okay, so I don't think that works either. But look, maybe there's other things that could work, but I'm not I won't say optimistic, because I wouldn't be optimistic. I am pessimistic, as those will succeed. Okay, does the Gibbs rule assume what is to be proved? So this is the really important. And I think it helps just to look at this slide a little bit more and to think about it a bit more. I mean, the reason to think that there is some horrible question begging going on is because, of course, this thing is just, using the Born rule, just a probability density. So you're thinking, well, of course, everything works the way you've done it and so on and so forth. It was absolutely obvious. There was no need for me to go on about it for 40 minutes or something. I mean, it was just immediate from that. Okay. But the thing about that is it assumes there's nothing problematic about understanding psi squared as a function and as a probability density. I mean, if you do feel that, there's just nothing problematic about it, even in the Overton interpretation. And then in a way, of course, I've got nothing really to say. I mean, you already are totally happy with your understanding of probability. I don't have to add anything to it. Fine. So I'm really only addressing those people who find the idea of psi squared as something, really physical, like a field out there in space, which takes values in M. This thing exists. How on earth can that thing be a probability density? What does it mean? What does it mean for the amplitude of a state, the square of it, to be a probability? It's those who find it unintelligible. I'm really engaging with those who find this notion that probability is a quantity. Those who find that unintelligible. Engaging with that. Because to some extent I share it. To some extent I take it fine. I used to think, look, this is fine. We're used in physics to things that we thought we knew turning out to be something entirely different. colours. We think they are, but then there's these relative spectral reflectances and so forth. Sounds very different from what we thought, right? Or tastes. And actually, that doesn't seem right. Thoughts. Neural processes, that doesn't seem right. So we're used to this in physics, and lo and behold, here's another example of it. Probability, objective physical probability, has turned out to be something we didn't expect. Well, maybe I was just being a bit too open. But anyway, I mean, I sort of got that, well, this really doesn't seem to be good enough. So for those who find amplitude squared as unintelligible quasi-probability, can understand it as quantity, thinking about equal amounts of the wave function, or equal fractions of the wave function, which is, after all, fairly close to what Gibbs was talking about with his equal numbers in the ensemble, equal fractions of the ensemble. So you can use very similar words in describing things that are going on. Now, of course, once you do define these equal fractions of the wave function in this way, by finite frequentism, you deduce that they're equiprobable, and that therefore this thing is a probability. But that's following from finite frequentism. It's not assumed it from the beginning. Anyway, so that's my defense really against the question-begging charge, and maybe you will not be satisfied with it. We'll see. So does quantum probability always involve decoherence, and moreover, a degrees of freedom that are continuous? Continuous spectrum. So I think that's a very interesting and open question. I mean, I think an obvious thing to say along Bell's line is that all measurements are position measurements. If you're talking about anything like a macroscopic measurement, I think, yes, all probability that's ever measured involves decoherence. But one could imagine, nanophysics structures that are somehow performing measurements that are recorded in some way, and maybe much, much later we learn what that recording is. Such that it would be sort of hard to think that the measurement was made much, much, much later. You could wait 100 years or something. You think, well, the measurement was made. It was made by this little, nano-robot thing. And maybe it's just constructed in such an ingenious way that there's no decoherence as such going on. So I think there is an open question there. Sure, I think irreversibility, maybe that's how you say. If irreversibility is going on, then... But suppose that is a possible future technology. And suppose also people like to do finite dimensional Hilbert space, and they do all kinds of analysis and models one can construct and so on and so forth. Where one once thinks in terms of probability, and that whatever notion of probability is operating there would then not be this. Worry.
Very quickly, the cell decoherence doesn't define the cells, right? It just says that the cells need to...
It defines the manifold. It defines the basis. As a manifold, I think position based.
Right.
But when does decoherence take place? Well, almost always when you've got large numbers of degrees of freedom. So if you're really looking at microscopic systems, just a few atoms with some interesting interactions among them, then of course there may be no decoherence. And a lot of quantum computing is about preserving against, defending against decoherence, so that you can later on get interference effects involving different computational outputs. So, but now here's the thing. You will have noticed that I hardly ever really talked about decoherence. I mean, I just had this basis. I was making the point that it has to be continuous, but otherwise, when did decoherence ever come into it? Even when I forbade ever going to the other elements, it wasn't because decoherence will ultimately kick in and lack of, or failure of decoherence will kick in. And it was just that they ceased to be elements of the Hilbert space. So, why is decoherence needed? And I think, in a sense, this is right, that you can choose any continuous subjoint operator you like, and you can just write the quantum state as a wave function with respect to that spectrum and whatever else you want. You can do the same thing, and you will have a probabilistic structure in the quantum state. And you will have ensembles. And maybe that's just exactly right. I mean, I think in a sense, if that is the right way, and it totally vindicates those, and there are many who I have great respect for, who may be listening, in their view that quantum theory is fundamentally about probability. Because this would be a way in which quantum theory is indeed fundamentally and at every level about probability. But now, what happens though if you don't have the continuous variable? That's the thing. And then it becomes a bit different. But here's and it's in a way even more elegant. Take that simple finite dimensional Hilbert space, take a simple spin system, take a state, spin half particle, represent that state in terms of equiamplitude superposition. Any basis you like. Of course, there's an uncountable infinity of bases you could use that all would rotate about the central, the initial state, and you can rotate around it. But you've got an equiamplitude representation, and you've got an ensemble. So can you always, for any vector in a Hilbert space, finite dimensional Hilbert space, you always find an equiamplitude, a basis in which you have an equiamplitude superposition? You can. I mean, you proved it. So, if you prove it, well, I'm embarrassed, but I claim that you can. It seems to me intuitively a bit of work to. So what does that tell you? It tells you that, yes, you even have these probabilistic ideas going on at level and blah, blah, blah. And further, you get the premises of Gleason's theorem for free. Because essentially, the premise was additivity. Now, the reason for Gleason's theorem, why that's problematic, of course, is additivity in that context is equivalent to non-contextuality. A lot of people think, well, that's, it's not really right. But you get this non-contextuality for free with finite frequentism, again. So there's interesting questions about what happens when you vary the state. How do the problems change? But I'm going to be on my list, and I've got enough on my list, so forgive me, I'm going to go back to my list. So that's just a comment about generalizing. So other sorts of questions, I've lumped them all together. So how does standard critiques of finite finite frequentism, can we be sure it's a form of frequentism at all? And this is particularly the case if it turns out that absolutely every one of the usual difficulties just goes away, poof, maybe the right thing to say, well, look, that's because it's not frequentism. So there's a little bit of a worry about doing too well on this one. I'm going to come across with that one. But just so you see, just take the most straightforward and standard one that we teach everybody, first undergraduate tutorial relating to probability. What about a single case probability? How does frequentism make sense in a single case? But you've got some incredibly rare atom. It's got a number of 150 or something, and it's about to decay. Well, it decays, right? So you've got an ensemble of one. Where's your relative frequency? Where's a meaningful notion of probability? Of course, in a way, that must be a reductio ad absurdum of finite frequentism. At some level, it must be, but it's not. Not this one. Why not? Because that atom decaying, of course, what it's really doing is producing an inordinate amount of branching, and branching that continues over time. It's quite interesting, actually, what it is doing from an Everettian point of view. So perhaps to simplify, if we just take a simple example of an ordinary quantum experiment, just a single outcome experiment, you've got an ensemble right there. And you've even got a large ensemble if you are counting microstates which have very similar, identical macrostates, but they differ microscopically. Right. So you're going to have very, very large numbers of macrostates corresponding to each experiment. So you only do the experiment once. It's a single case in that sense, but from an Everettian perspective, of course, you've got a huge ensemble produced right there and then, and you've got relative frequencies correspondingly. So So, I mean, that just illustrates how it gets around. And most of the usual critiques of frequentism, especially finite frequentism, are bound up with this, an example of a reference class problem. What is the reference class? Is there a reference class? But that exactly is what my whole discussion about consistency is about. It's about how do you reconcile different reference classes. Okay, so now, is it a form of frequentism at all? Well, here's a nice quote. So he's saying it's got many attractive characteristics. Okay, it is reductive analysis of primitives are well understood. It must be right. Amplitude, I must think, is well understood. The problem of measurement is a big problem, but we know what amplitude is. If we don't know what amplitude is, we're not going to do that. You've got to go and do some more reading here. We know what amplitude is. Okay, and that's the main thing. Well, there's a further worry now that what about decoherence? So, is that well understood? Well, I sort of think it is. So there's a complaint now that decoherence theory presupposes probability, presupposes the Born rule, and so forth. So that's a whole debate I won't get into right now. Anyway, it apparently makes the epistemology of probability straightforward. I want to leave that till the next one. Unlike the classical and logical theories, it appears to be about the world. Well, it surely is. It's about the worlds. It seems to be inspired by actual scientific practice. Absolutely, because it really is inspired by Boltzmann and Gibbs. You forget about Everett. You might think, well, that's an example of bad practice or something like that. But it's certainly, you're not going to say that of Gibbs or Boltzmann, and it's inspired by them. And it seems to, yeah, okay, good. So we come back to the epistemology. Well, the thing about epistemology, why would one ever think that finite frequentism is easy epistemologically? Answer, if you know what the ensemble is. And because it's actual and finite, you know what the ensemble is. And once you know what the ensemble is, the epistemology is done. But who on earth, except for extreme positivists, would think that the ensembles relevant to probabilities are actually observed? In any sort of, I don't think I've read certainly not von Mies. The ensemble is whatever exists. And we only observe a little bit of it. So, as soon as there's a gap between the ensemble that defines what the probability actually is, the objective physical probability actually is, and the ensemble that we know about, the one as soon as there's a gap between the two, then it's horribly complicated. Extremely difficult. So, exactly the same in my Gibbsian quantum frequentism. So, and that, of course, takes us on to the question of the epistemology of chance. Now, I hope nobody's puzzled as to how this really works, in that because we do experiments repeatedly, we build up by 10, a large number of experiments, we build up an ensemble, which is now enormous, got m outcomes for experiment, times that's m to the n different macrostates, let alone numbers of macrostates that have then been produced in the multiverse at the end of the n measurements. We only have access ever, always, as an epistemic community, we have just one in an ensemble. But that one in an ensemble will, of course, include records of all the others. It will be one of this vast ensemble, include all the records of the other outcomes, and so forth. That proceeds as it normally does under Everett. And another aspect to it about is this really frequentism. If you think of Boltzmann or Gibbs as hypothetical frequentists, which is what they were, the ensemble was imaginary. They only had access to one member, if that, namely, everyone was actual. Okay, so it's rather typical, actually, of frequentism. It's a horrible pun, but it's typical of frequentism that you only have access to one element in the hypothetical ensemble. how could it be otherwise? Because if it's a hypothetical ensemble, it's not like 2 or 3 of them are going to be actual. 500 of them are going to be actual. It's a hypothetical ensemble, so most sort of one. It might be worth just connecting with Gibbs' actual writings here. I think we don't have time. I really should. Oh, I've gone over. So I'll just stop. Sorry about that. I've really got to stop. This is to apply only to the Everett interpretation. Well, pilot wave people, it's yours for the taking. Make of it what you will. And especially those opposed to the idea of quantum non-equilibrium in pilot wave theory, so opposed to Valentini, who insists that the principle that the Born rule must apply to pilot wave theory or Brownian mechanics. Maybe this will be. I'm skeptical because you've got to worry about those additional degrees of freedom you've just introduced and what they are doing and statistical structure associated with that, which can be maybe quite different from anything in the state. So thank you very much. Sorry, I've just gone a bit over time.